If you think about this, the first thing we need to know is the electron configuration of the atom that we're talking about, the parent atom. And then we need to think about the principles that we learned that have to do with the stability of ions. Electron configuration of ions we learned for groups 1A and 2A, and 6A and 7A is related to gaining or losing electrons to get to a noble gas configuration. For the elements in the periodic table in the region of the metals of 3A, 4A, and 5A, we said that they can't reach a noble gas configuration, but they can reach a pseudo-noble gas configuration, and they can reach an inert pair configuration, and those metals, relatively heavy metals, will generally form those things. So we will apply the rules that we have for stable electron configurations to figuring out how many charges of what kind is needed for a particular atom. So let's have a look at this. First of all, barium, Z is equal to 56. If we find barium in the table, okay, barium is in the 6th period, 1, 2, 3, 4, 5, the 6th period, and it's in the 2A group. So the 6th period and 2A would mean that its outermost electron configuration would be 6s2. 6s2. And therefore it is 2 electrons beyond the closest noble gas, right, which would be xenon. Z is equal to 54. So the most reasonable way to expect a group 2A metal like barium to form an ion is to lose 2 electrons, to go back to the xenon configuration. So we would expect this to be barium 2+, which would have a xenon configuration having lost these 2 electrons. Okay? Nothing too surprising there. We've seen that the group 2A metals form dipositive ions, and this is the reason, the underlying reason for them doing this, to form a stable electron configuration. If we look at oxygen, that one is in the 2nd period. It is in group 6A, and therefore its electron configuration is 2s2 2p4. Okay? And from its position, the nearest the nearest noble gas to it would be neon. And it would need to pick up 2 electrons to get to the neon configuration. And if it did that, it would then have 2 more negative charges than positive charges. So this is the reason for the oxide ion having 2 negative charges, and it would have a neon configuration. Okay? Again, nothing new there. Questions on either of those? Yes?
That's not the full reaction point, though, is it?
Well, no, it's not. You're right. I should write it out. Oxygen goes to O, oxygen plus 2 electrons goes to O2 minus. You're right. What I was trying to do is to step you through the thought process of how you decide on what the charge on the ion must be based on how many electrons have to be added or lost to get to the noble gas configuration. Is that part of it clear? Sorry, I should have been more diligent about writing out the reactions. Okay, let's get to the last one then, which is one of the ones that we talked about. It's in the group that we talked about last time. It's lead, and lead is also in the 6th period, like barium was, but it's over here in group 4A. Okay? So it's in that group of main group metals that can't form a noble gas configuration, but they can form a pseudo-noble gas configuration or an inert pair configuration. So if we look at this as 6 period, it's group 4A. So it's electron configuration. Now here's where it's worthwhile to be sure that you follow the periodic table. Because in 6A, as you look at the process here, here is the 6s1, 6s2. Now notice what the periodic table does right there. It's 55 and it jumps to 72. And there's a line that points down here to the 4F. Everybody see that? Okay, that's the filling of the 4F, which comes in after the 6s. Remember we said as you got higher up in the value of n, there is extreme overlap between the subshell energies. And then they get closer and closer together. So what happens here is once you fill the 6th S, evidently the next available subshell is the 4F as in Frank. It's down here. So as we go across towards lead, it's 6s2, then 4F, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Wait a minute. Lanthanum, well, this table is a little bit different than some. The one in your book puts lanthanum up here. It would be 3, 4, 5D1, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 14 would be the 4F ones. Lanthanum occurs at a position where there are several several subshells of the same energy. So let's see if we can work this out. We have 6s2, and the way that table is, it's 4f14, and then we would go back to 72, which is hafnium here. See, 71 is lutetium. We go back up to hafnium, just following the numbers. You don't need to know the names. And we would start filling the 3, 4, 5D. We would fill the 5D10 when we got over to mercury. Okay? 5D10 would be mercury, and then we have TL, which is thallium, and then lead. So this would then be 6P2. And this is for lead atom. So it gets pretty complicated down there. But fortunately, we don't have to worry about the 5D10. It's filled so it becomes core. Or the 4F14, it's filled so it becomes core. So the only thing we have to worry about really are the 6P2 and the 6S2. And remember what we said was that we could have the loss of all of these. So we could have PB goes to PB 4 plus 4 electrons. In this case, the PB 4 plus would have the pseudo-noble gas configuration of, it would be xenon 4F14, 5D10. Okay, that would be the pseudo-noble gas config for lead 4.
Would it be XE or RN?
No, it has to be XE. RN is in the same period. It's at the end. It has a higher Z than lead. And that would mean if you went to RN, you would have to add electrons to the lead, and metals don't form anions. They form cations.
Aren't you supposed to go to the nearest noble gas?
Yeah, the nearest noble gas is Rn, but you can't just blindly do that. Okay, we're talking about a metal. It's not going to form 1, 2, 3, 4, 5 negative charges. That wouldn't be stable anyhow. Okay, so what you have to remember is the stuff we talked about last time. 3A, 4A, 5A in this region form noble gas, pseudo-noble gas, and the inner pair configurations. They don't form anions. Yes?
How would you know if it is lead is 4 plus and lead 2 plus? How would you know the difference?
Okay, you don't know the difference. What you know is it'll form both of them. You should expect it to form the pseudo-noble gas, 4 plus, and the 2 plus. Both of them should be possible. And I'll write that one. For that one, we lose just the 6p2s, okay, because of the stability due to the penetration effect of the 6s2. So we would have Pb going to Pb2 plus 2 electrons, and this would be xenon, 4f14, 5d10, 6s2. Okay, so we would assume that lead could form both of them, and in fact it does. It does. There are lead 2 and lead 4 compounds.